Hello everyone, welcome to this video. This time we'll be solving the quantum harmonic oscillator, which is basically just the Schrödinger equation, but with the potential of the quantum harmonic oscillator, which is just the mass of the particle divided by 2 times the frequency of the oscillation squared times x squared. So we want to solve the Schrödinger equation for this potential. Why do we want to do that in the first place? Just like in quantum mechanics, in classical mechanics, in quantum mechanics, the harmonic oscillator will have many important applications, and it also has a lot of pedagogic use. It's very good for learning when you're learning quantum mechanics. There are many concepts that can be explained very well and understood very well by studying the quantum harmonic oscillator, and also many of the mathematical procedure that we have to use in order to solve this oscillator will be very useful in some of the things that we will do in the future. So that is why it's very important and very good to solve this there. So let me now write the Schrödinger equation. So it's just the familiar form that I hope you remember. Now instead of the potential, we write down, just V instead of V, we write down this potential of the quantum harmonic oscillator, omega squared x squared divided by 2 times the wave function. This is obviously the time independent Schrödinger equation. I'm omitting this factor of x here just for simplicity, but as we talked in previous videos, this will be the time independent unless we explicitly say so. So this is going to be energy psi. Okay, so how do we solve this? Now the main thing to do is just begin by factoring out this 1 divided by 2m, because when we do that, we will see that what we get is just h bar, and we can write this minus as having this divided by I. So write this as h bar divided by I squared, and we can go actually further and put the derivative operator in here too, and have all of that squared. Plus, and when we factor out the 1 over 2m here, we get m omega x, all of this squared. I just factor out 1 over 2m here, and we have all of this acting on psi. Now, looking at this, we can see that this term in the bracket is something squared plus some other thing squared. If these were numbers, we could just say, okay, so let's say we have numbers a and b, which are real numbers. We know that a squared plus b squared is just a plus ib times a minus ib. And why is that? This happens because, well, when we multiply with a squared minus iab plus iba minus the I squared gets another minus, so it is now plus b squared, and this is going to be this right here because minus iab will cancel out iba, and this happens because ab is the same as ba. So when we have this right here, we say that a and b commute because a times b is the same as b times a. That is true for all of the real numbers. However, that is not necessarily true for operators. So if we have some operator, I don't know, big A multiplying big B, this is not necessarily the same as B times A. So we can't really just factor this out, this expression here, in this form, because we don't really know if our operators in here will commute. So I hope you have seen a bit of commutators in the past. If not, we will dedicate some more time to it in the future, and it's not really that important for now. It's just important that you understand this concept. So now what we are going to do is, although we don't know if it commutes, it is worth taking a look at this. So let's say, okay, maybe it doesn't commute, but let's just see what happens. So let us take a look at what is in all of that. So get 1 over 2m, and let us write what is in here as h bar divided by I dx plus m omega x times I, and all of this multiplied by h bar divided by I d over dx minus I m omega times x, and all of this is acting on psi. So we don't really know if this is the same as what is up here. I just want to make that very clear. But since it is quite similar, and if everything commutes, it would be the same. So let us just take a look at it. Maybe it doesn't commute, but maybe there is some relationship that we can use, some commutation relationship. So let us now, well, there's several ways to do that. I need some more space, so I'm just going to go to the next page, I think, so that I can solve this and I don't have to be going back and forth between the slides. Okay, so let's just multiply. So we get this 1 over 2m outside, and let us now multiply this first one with this one. So we just get minus h bar squared d squared dx squared. Then we get this times what is here. So the i's will cancel out and we get minus h bar m omega. And now be very careful, please. Sometimes when you're just starting out, it is easy to commute things like just without thinking about it. So don't write just x and d by dx, right? So you have to respect the order in which things come. We can commute now these constants because constants are just real numbers and they commute. So we can just write them out in front. But the d by dx comes before the x. So we write d by dx of x. But it's not just of x because this is also acting on psi. So do not go straight ahead and just say, oh, okay, that's 1. Okay, don't do that right away, okay? So, well, now we continue and we multiply this by this. So the i's will once again cancel out and we get m omega h bar, and now comes the x, which is now outside of this derivative. And finally, the last term is just going to be m omega x, all of that squared. And all of this is acting on psi. So let us now make all of this act on psi. So in order to do that, I'm just going to erase this here and just put it inside, okay? Just to save some time, I'm going to put this psi here. I'm going to put it in here in the derivative. Deep psi and psi here. Okay, so let us now take a look at this. The first term, this thing right here, there's nothing much to do there. So let us just do it as it is. These constants will also stay there. Now we have this derivative though. So let us now do it. It's a product rule. So we take, as you know, the derivative of the first time the second one without deriving plus the other way around. So it's going to be 1 times psi, so just psi, plus x times d psi dx. And then we have this term right there, which is just, I'm going to change the order of these constants just to make sure that they are the same. So it's going to be h bar m omega times x d psi dx plus, well, the same thing here. So we only really changed here where we derived. And now if we take a look at this term right here will cancel out this in here. So what we will get is the following. We get, well, this first one will be unchanged. Oh, damn it. Okay, sorry, there we go. Okay, so I meant to, there we go. Okay, but this term right here will still exist. It's just minus h bar times m times omega times psi. These two canceled each other. They are the same. You can just multiply this and check. It's immediate. And then we have this last term, which is just m omega x squared times psi. So now if we separate this, I'm just going to put this term and this term together, and this third one will go outside. So I'm going to have 1 divided by 2m times minus h bar d squared psi dx squared plus m omega x squared psi. And now outside, I'm going to write minus 1 over 2m times h bar m omega psi. But here the m's will cancel out. So what we get is just minus h bar omega divided by. Okay, so this is what we got when we just saw what happens when we multiplied these two things. So what is this? We can see that this right here, this is just our Schrödinger equation, right? This is just the Schrödinger equation for our given potential. So we can actually just go ahead and write, instead of this, we can just write that this is the energy acting on the wave function. So what we would have here is that this entire thing, let's actually go back a slide. So it's this right here is just going to be E times psi. Remember, because we used that this right here is just E times psi. That's what we did. Remember, just this here is the same as this right here. So that is E times psi minus h bar omega divided by 2 times psi, or we can rewrite it as E minus h bar omega divided by 2 times psi. Now this is a very, very, very important result, because we can see that although they do not commute these two terms here, there is a relationship. They do, if it is the Schrödinger equation, but with this extra term, which lowers your energy. So let us now name these things. This right here we will call A plus, and this right here we'll call A minus. Why? Because this has a minus sign and this has this plus sign. Now these are very important operators. In the future you will see that they will call the destruction and creation operators, but for now they are just these operators. So what we can see is that, and just to make sure, each one of these will also have 1 divided by square root of 2m. That has to go into each one of those. Okay, so there's going to be 1 divided by square root of 2m in here, and also in here. Okay, so that we take into account this 1 divided by 2m that is multiplying them. So what we did here is that we found that A plus A minus is going to be E minus h bar omega divided by 2 psi. Now this might be a little weird, like why are we doing this? But these operators, as you will see, we need to know how they behave, because they will allow us to determine the wave function of this quantum harmonic oscillator in a very, very easy way. So I'm going to now put this in the corner because it's a very important result. X, there we go. Okay, that's important. Oh, I'm actually covering up with my camera. Let me move it somewhere else. I'm going to put it right there. Okay. So now we saw what happens when this first one multiplied the second one, but let us now take a look at what happens the other way around. So basically, we had A plus, A minus. Let us now take a look at A minus times A plus, which basically just means 1 divided by 2m h bar over I d by dx plus, sorry, minus, because this time the minus goes first, minus I m omega x, and now the same but with a plus sign. And all of this acting on psi. So this is A minus A plus. Oh, did I write this? Yeah. There's supposed to be a psi in here. That's very important, okay? Because these operators are acting on the wave function. Okay, sorry that I left it out. Okay, so the same as before, we have to do this multiplication. and it's going to be basically the same. In fact, you could do this yourselves, but I just want to make sure that if there's anyone out there who's not entirely sure, I want there to be something on the internet that you can use. So the first term is just going to be minus h bar squared d squared dx squared. The second multiplication will now be h bar m omega, whoops, very important, d by dx of x, and remember here will be the, in fact I can just go ahead and write it down immediately. I already did it step by step, so I'm just going to put the wave function in there right away. Now we must multiply this with this, so we get minus m omega x, well, and there's an h bar there, d psi dx plus m omega x squared psi. Okay, so now similar as before, all of this will be the same. And here we will have this, actually I only want to copy this. Now we have this product rule that we must do. We just derive this, so we're going to get, as before, just psi plus x d psi dx minus all of this. So now we will have also that this will cancel out this, but this time our the signs will be different. So let's look at this. We are going to get this times psi plus m omega x squared psi. So similarly as before, we will now separate this, because this right here and this right here are part of the Schrödinger equation, but this here isn't. This is an extra term that came from the commutation relationship between our two operators. So we're going to get 1 divided by 2m times minus h bar squared d squared psi dx squared plus m omega x squared psi. And we also have plus 1 divided by 2m times h bar m omega psi. But as before, the m's cancel out and we can just rewrite it as h bar omega divided by 2 times psi. And the same as before, this right here, this is just the energy, right? This comes from the Schrödinger equation. This is what we saw from here. It's just this right here. So let us now, where was I here? So we will now see that a minus times a plus acting on our wave function is going to be the energy times psi. Yeah, this by the way should cover the 2m as well. Plus h bar omega divided by 2 times psi. Or if we now factor that, we could just get e plus h bar omega divided by 2 psi. So this is the second very important result that we wanted to find, because now we see what this factorization looks like. So I'm just going to copy this and put it right next to the other result here in the first slide. Okay, those are, and as you can see, all we did was change a plus for a minus here, and we got that this minus is now a plus. So now that we know that, we know kind of how these things behave, but what do we actually do with this? I mean, so far, and this is what is kind of tricky about this method, it's not really hard what we are doing in terms of algebra, but it is kind of hard to be like, okay, and why are we doing this? And how did you think of this? And that is kind of the tricky part here. But it's going to make more sense when we get to the end. Because what this method will do is that we are going to exploit these operators to create all possible wave functions starting by just one known wave function. And you will see this very soon. So what we now want to do is, we know that some psi will be a solution to the Schrödinger equation. Now, I will claim that A plus acting on psi will also be a solution to the Schrödinger equation. Okay, and in that case, we want to see what happens to the energy of the wave function. So what is our Schrödinger equation? Let us write it down in one of these two forms. And the trick here is to use the first one. Okay, so we are going to copy this first part right here. So let us go here. I'm thinking about copying it. I think I'm going to copy it just so that we can have it. I'm actually going to copy both of them and just leave them in here in the corner. Okay, and I'm going to just draw a little line here so that it doesn't get confused with what we are going to be doing. Okay, so let us write down the Schrödinger equation. So using this first relationship, we can see that A plus A minus acting on psi plus h bar omega divided by 2 times psi is going to be the energy of this wave function, right? All I did was multiply both sides by this h bar omega divided by 2 term, okay, so that I left this energy alone. So I say, what I claimed is that if this psi is a solution, then this A plus times psi is also a solution. So let us check that and let us see what happens to its energy. So instead of psi, I'm going to write A plus times psi. And we want to see if it works. As I said, this is just a method that uses these clever tricks, so this better work somehow. Okay, so let's see what happens. If we just multiply this, we get the following. I mean, I'm just going to open these brackets right here and right here. And now what you can see is that there's an A plus multiplying from the left, both on this first term and also here, because this h bar omega divided by 2 is just a number, so you can just commute it with the operator. There's no problem there. So you can now factor out A plus from the left, and you get A minus A plus psi plus h bar omega divided by 2, and we can just leave this psi outside. There we go. And now let's take a look at what is in here, because we got this A minus A plus that is acting on psi. So it kind of looks like this second equation here. But the problem is, when we rewrite this, just as we did with the last one, we get that A minus A plus times psi. Wait, I want to skip a step here. We are just going to subtract this h bar omega divided by 2. So we get minus h bar omega divided by 2. All of this acting on psi. This is going to be e psi, right? So we see that we have this A minus A plus, but we don't have minus h bar omega divided by 2. We have plus h bar omega divided by 2. So how can we solve this? We want to get from this h bar omega divided by 2 to the minus h bar omega divided by 2. So we want to just sum, we want to add a term here. So we are going to want to have basically h bar omega, and from this we subtract h bar omega divided by 2, because when we do this, we are going to get the same h bar omega divided by 2. Okay. Now, we didn't do anything illegal here. I hope that's very, very clear. All we did was we wrote this term here differently, because we want to be able to use this relationship right here. So this times psi. Now, we are going to separate these terms just to make this clear. So now we get A minus A plus minus h bar omega divided by 2 acting on psi. And this term right here will now be outside, so we get h bar omega times A plus psi. But this right here, as we see, is just E times psi, right? This is just what is here. It's precisely the same. So we get A plus times the energy times psi plus h bar a plus psi, and we can rearrange this because E is also just a constant. So we can now write this as E plus h bar omega times a plus psi. And remember, what we started with was just the Schrödinger equation, but instead of having this psi, we wrote it as a plus psi, because we said if psi is a solution to the Schrödinger equation, then so is this a plus psi. So remember, this was just what is up here. In fact, I might just copy it and not just write it again. Oh, I meant this one right here, sorry. It's actually kind of tilted, but I think it's good enough. Okay, so this part right here, remember, is just the Schrödinger equation, but written in terms of these operators, a plus, a minus, and with this a plus psi wave function. So we see that this a plus times psi wave function does satisfy the Schrödinger equation, because this is the same thing, except that this time we have energy, energy prime, which is the energy of this psi wave function plus h bar omega. So what this basically did, what this means is that this operator a plus raises the energy of the psi wave function. Okay, so psi had an energy E, and now the wave function a plus psi, whatever it is, we haven't seen it yet, this has an energy E plus h bar times omega. So that is what we just saw here. I'm going to just talk about this a little bit more, because I know that this can be very confusing the first time. So what we did here is that we took the Schrödinger equation written in terms of a plus and a minus. If you are not sure, or you don't understand why this is the Schrödinger equation, then you have to go back in the video and see how it was that we derived it, right? It just came from this right here. We just rearranged this equation, and how we got to this in the first part of the video. And here we said, okay, if this wave function psi is a solution, then so should be, or I claim that a plus times psi might also be a solution. So we just wrote a plus psi everywhere instead of psi, and we just multiplied. Okay, and we just worked this algebraically until we got to this result. And we saw that the Schrödinger equation has the same form, right? But the energy is changed. So the energy is no longer just E, it is E plus h bar times omega. So that is a very important result. That is one of the most important things, because this is going to be an operator that raises your energy, and that is the whole point of this method. That is also why it's called this, the method of these ladder operators. Why ladder, you will see very short. Now let us do precisely the same, but this time looking at not a plus psi, but a minus psi. So let us now go to the other equation. Now you might think, why are we using this equation? Because remember, these are both valid forms or valid ways in which we can write the Schrödinger equation. Why did we go before for the a plus a minus form, and why are we going now for the a minus a plus form? And the reason is because when you do this one and you are considering a plus psi, you're going to get a minus a plus. If you had used this for a minus, you would have gotten a minus, and you don't really have a relationship for that. So that is why when we take this a plus psi, we want to use this form, and when we take the a minus psi, we want to take this form, so that when we do the multiplication, we can use the relationship of the Schrödinger equation in this operator form. Okay, so I'm also going to copy the Schrödinger equations here, because we are going to need them once again. I'm going to erase that. Okay, so let us now, same as before, rewrite this, basically just subtracting this h bar term. So we get minus h bar omega times psi. My pen is lagging a little bit. There we go. And this is going to be equal to E times psi. This is just the Schrödinger equation written in this way. And now let us take a look at what happens with this A minus psi solution. So A minus A plus, and now instead of psi, we write down A minus psi minus h bar omega times A minus psi. This is equal to the energy times A minus psi, right? So similarly as before, we just multiply here, we remove these brackets, and we can now factor from the left this A minus term. So we get A plus A minus times psi minus h bar omega times psi. And well, this is just going to be what we get from these. I mean, this is very similar to this right here, right? But we have this little problem that this is minus h bar omega, and this is not plus h bar omega divided by 2, because if we rearrange this, this is very similar to what we did in the last part. You have plus h bar omega divided by 2 psi equal e psi, right? But if we don't have plus h bar omega divided by 2, we have minus h bar omega. So just as before, what we have to do is, okay, we want to get to this h bar omega part. What did we do last time? Last time, we said, okay, h bar omega divided by 2 is just h bar divided by omega. So this time it's going to be basically the other way around. So we're going to have this h bar omega minus h bar omega divided by 2. Let me see. Yeah, there's a slight issue here. I think I copied something wrong. Oh yeah, there it is. This is supposed to be divided by 2. That's why I found this so weird. Okay, so let me just go back a step, because this is supposed to be divided by 2. Sorry about that. Yeah, that's why this was looking somewhat odd. Okay, so, but the problem still persists. We need it to be positive. It's currently negative. So the way to do that would be to take this minus h bar omega and add h bar omega divided by 2. So when we do this, we're going to get this minus h bar omega divided by 2. And so it's correct, you know, we're not doing anything illegal. So a minus, a plus, a minus, minus this whole thing here, all of this acting on psi. Now I just rewrote this, I didn't do anything weird. So let us now separate this. So we get a minus times a plus h bar omega divided by 2 times psi minus a minus h bar omega times psi. But this right here, similarly as before, we can now look at our equations here. In fact, the first one, this is just going to be the energy times psi. And then we have the second one, a minus h bar psi. So we can now rearrange this, because these are all constant. E, h bar, omega are all constant. So we get that E minus h bar omega times a minus psi. And this, just to make sure that we remember it, this is just what we started out with, which was our a minus, a plus, a minus psi, was it minus h bar omega, a minus psi. So when we take a look at the solution of the Schrödinger equation of a minus times psi, we get a state that has lower energy than E. So when we took a plus, we got a state with higher energy than E. When we took a look at this a minus, we found a state that has a lower energy than E. That is why this is called the method of ladder operators, because let us now visualize this. Let us now just visualize these ladder operators. Say we have this is going to be some state. Let's say we have this is going to be our psi, right? Some wave function, and it has energy E. If we apply now a plus on psi, then we are going to have this other state right here, And what is going to be its energy? Its energy will be E plus h bar omega, right? We just showed that. But what happens now if we apply this once again? If we do that, then we are going to get E times 2 h bar omega, because each time you apply this, you are just going to increase your energy by h bar omega. And you can go on and on. So you can see that your energy after, if you apply this n times, it's just going to be your base energy plus n times h bar omega. Okay, so it's whatever energy you had here, it's going to be n times h bar omega higher. And what happens if we begin applying the other operator, the A minus? Well, A minus acting on psi is going to give you a state with E minus h bar omega energy. It's going to reduce the energy. And if you apply it again, then I'm just going to draw it like this, then you're going to get E minus 2 h bar omega, and so on and so forth. So this is the way this works, and this is why it's called the ladder operators, because when you do this diagram, it actually looks like a ladder. That's why it's called like that. So, and what was the whole point of this? Because what we wanted was to find these wave functions. We haven't found them yet. And here is where the brilliancy of this method comes in. Because if we continue to lower the energy, each time you apply this A minus operator, eventually you have to get to some state where you just can't go any lower. At some point, you have to reach zero energy. If you apply this A minus enough, at some point you're going to reach some state, which is going to be the ground state, which we will call psi 0, where if you apply this operator one more time, it's just going to be 0. Okay? And that makes sense. I mean, you can't go to negative energy. So at some point, you will have to get to a limit. And there is not necessarily an upper bound. I mean, there's some things to discuss there, but for now, we are only going to be thinking about this lower bound. At some point, we just cannot go any lower in energy. So let us now take a look at this equation. What was A minus? A minus was just h bar divided by I d by dx. It's minus, so it's just minus I m omega x acting, and this is, well, times 1 over square root of 2 times n, and this is acting on psi 0. So this has to equal to 0. And now we have just a linear differential equation, and this is just much easier to solve. So just applying logic here, we managed to find this equation, which will be much easier to solve. So let us now solve it. So now we can just multiply by square root of 2 over m. It's going to just go away. So let us just rewrite this. We get h bar divided by I d dx of psi 0. This is equal to I m omega x psi 0. So let us now multiply by I and divide by h bar. So when we do that, this here will cancel out, and this I right here will turn into a minus. So we get, whoops, there we go. We get minus this, and this will be divided by h bar. So now we can separate the variables. Here we get the psi 0 divided by psi 0. This is equal to minus m omega divided by h bar times x dx. So let's now integrate this. So we get that psi 0, well, the logarithm of psi 0 is just going to be minus m omega x squared divided by 2h bar plus some constant a. And now let's exponentiate all of this. So we can find that psi 0 is going to be some constant a. I'm going to call it a again, but it's just some constant. Don't think it's the same as this one, but anyways, it's just a constant, times e to the minus m omega x squared divided by 2h bar. And this is it. Well, this a is just a normalization constant. We have to find it by normalizing, and we will do that in some other video, not this one, because I'm already going very long. I didn't want to go this long. But this is the ground state of the quantum harmonic oscillator. And we also know, well, we will find now actually what these energies are. So let us just, oh, I want to copy this. Let's go to the next page, because now we want to determine what are the energies of this state. We know what is the wave function. What are the energies of this state? So in order to do that, let us plug this into the Schrödinger equation. And let us do this in a smart way, because we have several ways to write down the Schrödinger equation. I'm trying to see if there's somewhere where this is a little bit less stretched. There we go, here. We know that if we apply the lowering operator onto this psi 0, then it's going to be 0. So let us choose this form of the Schrödinger equation. Okay, so let us now go here. Let us use this form of the Schrödinger equation, because this is going to make it a lot easier. So let's put in here psi 0 instead of just psi. So this right here will be 0, because a minus times psi 0 is 0. This is the lowest you can get. You cannot go any lower than that. There is no wave function. So this right here is just 0. So we get that the energy times psi 0 is equal h bar omega divided by 2 times psi 0. And take a look at this. We already found, let's call this E0 actually, because it is the energy of the ground state, not just any energy. So we found that the energy of the ground state just h bar omega times 2. And because we know that the raising operator, a plus times psi, this is going to give you an increase in energy of h bar over omega, we will know that the energy of some nth state is going to be the energy of the ground state plus n times h bar omega. So if we just factor this out, we get that the energy of this n state is h bar omega times n plus 1/2. So these are just incredibly important results. This is what we wanted to get to, and as you can see, it's really not, we didn't do anything too difficult. We barely solved the differential equation. Sure, we had to go through that weird thing in the middle where we didn't really know what we're doing, why are we doing this. But as you can see, once we get to this, it's really easy to do it. And now we can find any wave function we want. Let's say we want to find psi 1. Psi 1 is just going to be the raising operator acting on psi 0. Yeah, so let's go to the next page and just do this quickly. I know I'm going long, but it's okay. Okay, so psi 1 then is going to be the raising operator, which is just 1 divided by square root of 2 over m h bar over I d by dx plus I m omega x, and all of this acting on our wave function psi 0, which we already found, and it is some normalization constant times e to the minus m omega, it's not squared right now, it's omega x squared divided by 2 h bar. So we have to just solve this, which is super easy. All we have to do is to, well, multiply here. We have to now, well, let's do this by parts. So h bar over I, and we take the derivative of this, so we get minus m omega x. It's going to be 2x, but the 2 is going to cancel out the 2 in the denominator, and this times e to the minus m omega x squared divided by 2 h bar, and then we have the second term, just I m omega x times e to the minus m omega x squared divided by 2 h bar, and all of this times this constant a. But here, let's take a look at this. If we just write this I, if you multiply this by I divided by I, then this minus sign will be plus, and there will be an I right here. You can just check that right away. Just multiply up here and down here by I, and this h bar cancels out this h bar, so we just get plus I m omega x times this e exponential, which is the same that we have here. So this whole thing will just be twice im omega x times this constant a e to the minus just e to the minus m omega x squared divided by 2h bar, and this whole thing divided by the square root of 2m. But if we now rationalize this, we will see that our final result is just this constant a times the square root of 2 over m times I times x e to the minus m omega x squared 2h bar. So this is going to be, just let me double check it quickly because I want to make sure that is correct. So this is going to be our first state. I is a omega. Yes, that is. Oh, I forgot to write the omega. There we go. Okay, so this is going to be the first state, and we can just go ahead and find any others. I mean, to be honest, I wouldn't want to find like psi 50 in this way because it's very, honestly, it is kind of annoying, but it is very easy. It can be very tedious and very annoying, but it's easy. And that is something that is honestly quite surprising. So we could find any psi n wave function if we just apply the raising operator. We just get some normalization constant times our raising operator applied n times over this psi 0, right? Which is just going to be e to the minus m omega x squared divided by 2h bar, right? So, and as we already saw, this would have an energy of n plus a half h bar omega. So we found the energy levels and the eigenstates or the wave functions of the quantum harmonic oscillator using this algebraic method. And using this, you can find any other wave functions you want. As I said, it would be nice to have a direct formula, and that is what we will get when we use the other method, which, as I said, is much more brute force, but it is also quite convenient because it will be used later on when we take a look at the hydrogen atom. So that is it for today. I hope you liked this video. If you did, let me know in a comment, like, subscribe, and if you have any questions at all, just let me know and I'll make sure to answer them as soon. See you next time.